Hey guys, today we're going to be talking about lesson 4.5, and that's going to be working with isosceles and equilateral triangles. And we're going to continue with some proofs in this chapter as well. So our first theorem for today is going to be the isosceles triangle theorem. And that states if two sides of a triangle are congruent, being isosceles, then the angles opposite of the sides are congruent. So what this is saying here is we know these two sides, AB and BC, those are congruent. And this theorem is stating if that is true, then the angles that are opposite of them are also true. We can say that angle A and angle C, which these are referred to as base angles, those base angles are congruent to one another. So here we're using the sides, knowing that the sides are congruent, and using those opposite angles. Now, with our talk of proofs in chapter 4, there is a proof that goes along with this. So first, in our proof, we have our given statement that says xy is congruent to xz. And we also know that xb bisects angle yxz. So we've written that in our proof. We're in our phase 1 right now. I'm also going to draw that in our picture. So we have xy is congruent to xz. And so right now we are working with, we have three triangles in this picture. We have the large triangle here that I've highlighted in red. And then we also have, which is an isosceles. And then we have our triangles here on the left and the right side. Okay. So right now, if we focus on that larger triangle, we do have an isosceles triangle. Okay, we have two sides, at least two sides are congruent. But as we move into phase 3 of our proofs, we're going to use this term bisects. And it said that XB bisects this angle here at the top. So we know that each side, that angle is congruent. So we have angle YXB is congruent to Z, angle ZXB. That is by the definition of angle bisector. All right. And part of phase 2 is also using the picture. And here we have our stacked triangles. They are beside each other. So this line down the middle, that XB, that side, is reflexive. So step 3, we have XB is congruent to itself, XB, through reflexive, our reflexive property. And now we have enough information to prove that the two triangles on the left and the right side are congruent. So for step 4, triangle YXB is congruent to triangle ZXB. And our reasoning here, we have two sides, two pairs of sides, one pair of angles, and that angle is included, so we have side angle side. So we completed the first part of this proof, the first 3 phases, much like in chapter 4a. And then in our previous lesson, we talked about using CPCTC. So here our proof is an angle y is equal to angle y, z. So we are taking one of those corresponding parts and we're saying that those corresponding parts of the congruent triangles are congruent. That's CPCTC. So we are proving that y is indeed congruent to z, which is our theorem for an isosceles triangle. Okay, and there we are looking at the large triangle. Okay, now let's look at how we're going to use this in some of our examples. We have two scenarios that we will run across. And in the first scenario, we have the vertex angle. So that angle between the two congruent sides, also known as legs, is called the vertex angle. And our second example, we do not have the vertex angle. So first we're going to talk about an example using the vertex angle. We know that the measure of angle 2 is 8x plus 11. So down here for angle 2, we're going to replace that with the expression 8x plus 11. And through the theorem that we just looked at, we have our congruent sides. Their angles opposite of them are congruent. So actually, both of these angles will be 8x plus 11. Yeah, those are going to be congruent there. Now that we have an expression or value for all three angles, we're going to use the triangle sum theorem from chapter 3, and we're going to add up all three angles. We're going to take the vertex angle plus the two base angles, which here they are both 8x plus 11, and set this equal to 180 degrees. All three angles of a triangle add up to 180. And from here, we will combine our like terms, combine your x's, combine your constants, where we get 16x plus 68 equals 180. And then we will solve for our x. First, we'll subtract 68 from both sides. We get 16x is equal to 180 minus 68 is 112. And in our final step here, we will divide both sides by 16, getting 7 for our x. So here we used our theorem of isosceles triangles, knowing that those base angles are congruent, they're the same, and along with our vertex angle, adding those up using the triangle sum theorem to solve for our x. Moving on to example 6. Here we are missing our vertex angle, which is okay. We know our two base angles are located at 74 and angle 2. And I want to replace angle 2 with the expression 8x minus 6, coming from the directions here. So here, because these are two different values, 8x minus 6 and 74, they're two different expressions, we need to set these equal to each other. 74 is equal to 8x minus 6. And we will solve for our x, we will add 6 to both sides. 80 equals 8x. Divide both sides by 8. And we will get 10 is equal to x, or turn that around, x is equal to 10 here. So the two examples you may run across for problems using this isosceles triangle theorem will be if we have the vertex, we want to use the sum of all three angles is equal to 180. That is your triangle sum theorem. If we do not have the vertex, we want to set the two angles equal to each other. We know that they are congruent. All right. Now we also have the converse of the isosceles triangle theorem, so everything's sort of is backwards. Here we're going to start with the angles. We know that the angles are congruent. And this reads, if two angles of a triangle are congruent, then the sides opposite of them are also congruent. So here, we know that our two angles are congruent to each other. So now we can say the sides are also congruent. All right. We're going to look at a quick example using the converse here. Example 7. So we have our two angles, our base angles, and the sides opposite of them we can say are congruent. And by showing that, it allows us to set this up as 2x plus 20 is equal to 6. We can set those two sides equal to each other in order to solve for x. And as we solve for x here, you're going to see that our x value does come out to be a negative number. It comes out to be -7, which is okay. X can be anything, as long as when we substitute that -7 back in, it does equal a positive value, because here we're representing side lengths. So x can be anything, as long as when it's substituted back in, it does represent a side length, a positive value there. Okay? So example 7, we're using the converse. Okay? With example 8, you see these multi-step problems a lot. And here, we've worked with some multi-step problems back in chapter 3. And you're going to see some here again. We have actually two triangles. We have this gray triangle at the top that I've highlighted in blue. And then you have this black triangle towards the bottom that I've highlighted in green. And just looking at this, we're trying to solve for x. And we don't have too much information given to us in that first triangle, that gray triangle. All we know is that the two angles here at the bottom are both x. These are both x and x. We do not have a vertex angle like example 5, so we need to find that vertex angle in order to find our x here. What we do have is we're going to use this triangle at the bottom, and we know that we have another isosceles triangle. So both of these angles are going to be 58 degrees. Okay? Both of those base angles are 58 degrees. And we're going to use those base angles to find, I want to call this vertex angle Y. So we're going to use our triangle sum theorem. Y plus 58 is equal to 180. We combine our like terms. Y plus 116 is equal to 180. We will solve for Y. And we subtract 116 from 180, and we get 64. So the vertex angle here is going to be 64 degrees. Now we're going to use that 64 to find the vertex angle of our triangle on top. I don't know if you guys saw this, but we do have a 90-degree angle here. So we know that those two angles are complementary, and that will allow us to find, I'm going to call this vertex angle Z. So if I take Z and the 64, and their sum equal to 90 because of complementary, we can subtract the 64 on both sides, and our Z here is going to be 26 degrees. And now we have enough information to solve for the x's here, our base angles. We can take our vertex angle 26, add those to our two base angles, which are both x, and complete this with the triangle sum theorem. We have 2x plus 26 after combining like terms. We subtract the 26 from both sides, and we get 154. And we divide both sides by 2, and our x will be 77 here. So our final answer here would be 77. So this is a multi-step equation where we have to use concepts from Chapter 3 with triangle sum theorem, as well as concepts from Chapter 1, knowing that those two angles are complementary. Together they form a 90-degree angle. All right, two more things that we're going to look at here. Theorem 4.5 we're going to be using later on, and it says, if a line bisects the vertex angle of an isosceles triangle, then the line is also the perpendicular bisector of the base. So here we have this large triangle in our picture is an isosceles triangle. And we have a bisector. And what's unique here is that this bisector is a perpendicular bisector of the base. So it's perpendicular. There's a 90-degree angle that is formed. And we also have a bisector of a segment bisector, which we know that those two halves are congruent to each other. Then we have some corollaries. Corollaries are theorems branched off. So corollaries are just branches of a theorem here. And these are specifically looking at equilateral and equiangular triangles. Our first corollary says, if a triangle is equilateral, it is also equiangular. Our second corollary says it is the converse. If a triangle is equiangular, it is also equilateral. So isosceles triangles and equilateral triangles have a very similar relationship to squares and rectangles. A square is a rectangle. A rectangle is not a square. You've probably heard that statement before. Isosceles and equilateral have a very similar relationship. Equilateral is isosceles. Isosceles is not necessarily equilateral. So they have the same properties here. One thing I want you to take away is that in an equilateral triangle, all angles are 60 degrees. That's true for equiangular as well. Equilateral and equiangular, all the angles are 60 degrees. And that is because in order for all three angles to add up to 180 and be the same, they would all have to be 60. 60 plus 60 plus 60. They're the same and they add up to 180 degrees. All right? All right, guys. Take a look at the practice. Complete the quizz's homework check. If you have any questions, be sure that you get in touch with me. Have a good day.